Hello, welcome. Today we're looking at topics 210, which is inverses of exponential functions, and topic 2.11, which is logarithmic functions. So let's recap just a little bit about what we know about the general form. So that general form of a logarithmic function is right here, where we have f of x being the function value, and that is going to equal a log b of x. Remember that b has to be greater than 0 and can't be 1, and a can't be 0. So as we look back at what we know about inverses, we talked about in the last lesson that exponential functions and logarithmic functions are inverses with each other. And so according to the characteristics of inverse function, then we should be able to expect those same characteristics to hold true for exponential and logs. And what I mean by that is if I look at the input and output values of an exponential function, then they should become the output and input values of the log function, right? And why is that? Because the domain and range trade places. And I'm going to do the double arrow. So what was the domain becomes the range. What was the range becomes the domain. So that's that basic overall characteristic that we have learned in previous lessons. So also recall from earlier lessons when we talked about exponential functions over equal width input value intervals, then the output values have a multiplication to it. So the output values change multiplicatively. So the input values change by an equal distance, so you're adding, and then the output values change multiplicatively. And if you recall from Algebra 2, that logarithmic functions, that we just reverse the input and output values as we were looking at that graph. We also talked about that when we looked at inverse points and stuff in that lesson. All right, so now we're going to see how the input values are changing and the output values are changing. So in this particular table, so we have our input values are our x and our output values are your f of x. We're going to look and see if we can figure out what's happening to each of those. For instance, I can see that if I add 2 to 1, I get 3. And then if I add 2 to 3, I get 5. And if I add 2 to 5, I get 7. So we can see that the input values are changing additively. That's equal spaced. But then if I look over here at this side, then I could do times 2, and that gives me my 4, times 2, and that gives me my 8, times 2, and that gives me my 16. So the output values are changing multiplicatively. So we multiply by 2 each time, where here we add by 2 each time. So this is the basic characteristics of behavior for this to be an exponential function. Okay, so now we're going to look at the next table. And what we should be seeing from the next table is that I'm not just adding over here to get these. This time I'm multiplying by 2. So 2 times 2 gives me 4, times 2 gives me 8, times 2 gives me 16. So the input values are changing multiplicatively this time, while the output values, if I add 2 to this, I get 3. If I add 2 to this, I get 5. If I add 2 to this, I get 7. So the output values are changing additively, equal spaced. Okay, so those are the things that we're looking at as we classify. So in example 1, I'm going to ask you to do what we did here. So check and see if this is increasing additively or multiplicatively. And if this is increasing additively or multiplicatively, then you should be able to state which type of function it is, exponential or logarithmic. All right, so let's do 1A together, and then I'll have you pause your video so you can look at B, C, and D and see how you can do. All right, so if I look at this, I see these are equally spaced intervals. If I add 1 to 1, I get 2. If I add 1 to 2, I get 3. If I add 1 to 3, I get 4. So the inputs are connected additively. The outputs, if I multiply 16 by 1/2, I get 8. If I multiply 8 by 1/2, I get 4. If I multiply 4 by 1/2, I get 2. So the output values are changing multiplicatively. So the x's are changing, and let's say the x, or the input, are changing additively by 1. And then y, which is the output, is changing multiplicatively by 1/2. So by this being additively and then multiplicatively, it is an exponential. All right, so that's what I want you to do for B, C, and D. So go ahead and pause your video. Okay, so let's look and see how you did. So remember, you're looking if the intervals, if you can add to get that uniform width, equal width intervals, or multiply, so you're increasing multiplicatively. So in this case, I can add 1 to each side, so that's adding on the inputs, and I can multiply each side by 1/2, so that's multiplying on the outputs. So when the inputs are additive and the outputs are multiplicative, then it's an exponential function. On B, I can multiply each one of these by 3, so it's multiplication for the inputs. I'm adding 10 to each one of these, so it's addition for the output, which means the inputs are multiplication, the outputs are addition, so that's logarithmic. On C, on the input values, I multiplied each by 10, but on the output values, I also multiplied each one by 2. So since both were multiplicative, then that's a neither situation. So the input is multiplicative and the output. There we go, is multiplicative. On the last one, D, I can multiply each of these by 2. I can add a -3 to each of these, so multiplicative on the input, additive on the output. So input is multiplication, output is addition, so this is also a logarithmic function. All right, so on example 2, select values of several logarithmic functions are shown in the table. So we've already done our first read. We're going in the second read. So we can see selected values of several logarithmic functions are shown in the table. For each table, find the value of the constant k. So as I'm looking through this table, then I'm looking for what is the k, to figure out what. Okay, so on this example, we are going to find these missing k values. And so these are informations from a logarithmic table. And so what we're trying to do is figure out what is the pattern to be able to figure out the x value where k is, where that constant value is. So if I play around with the numbers and I kind of, I'm looking at my x values, then I can kind of see a pattern develop. If I look at the number 1, I'm going to kind of try some numbers out here. So I'm going to say 2 to the 0 power, anything to the 0 power is 1. And then I'm going to say 2. And then I'm going to do 2 to the first power, which would give me that 2. So now we don't know what k is yet, but if we follow through with this train of thought, this is 1, 2, so now it's 8. And so 8 is going to be 2 to the third power. And then we can look at this last one, which is 16. And 16 is 2 to the what power? Fourth power. All right, so if I see my pattern is powers of 2, then I should be able to come back in here and figure out what k is. So we have to the power 0, 1, something, 3, 4, so that's got to be 2 to the second. And 2 to the second equals what? 4. So now we know that k equals 4. Here, where my k is, so I know that this one, if this was 2 to the 1, this has to be 2 to the 2, this has to be 2 to the 3. So 2 to the 2 equals 4, so that's what my value of k has to be. So that's kind of pretty straightforward. So if remembering that this is a logarithmic function like we just talked about, then if this is the base of the exponent, this had to be the base of the log. So if I put my first x value in here for the argument, then I can think 2 to some power equals 1. Well, what does this something have to be? It has to be 0. But what did we need it to be? We need it to be a positive 1. So that means I would come back up here to my basic log equation, and I'm going to add 1 onto it and do a little bit of a vertical shift to my logarithm. Now, I'm not asking you to actually calculate the equations right now. I just kind of wanted you to see how all of this is tied back together. So what I would like for you to do at this point is to go to part B, and I would like for you to lay out your argument for the x values to figure out what k is. All right, pause your video and let's see how you do. Okay, so I played around with numbers here, and I kind of came up with 3 to the 1 power times 2 gives me 6. 3 to the second power is 9. 9 times 2 gives me 18. 3 to the third power is 27 times 2 gives me 54. And 3 to the fourth power times 2 gives me 162. So I can use that pattern to set up my value, and then I can find k by using that pattern, because if this was 3 to the 1, then this one is going to be 3 to the 0 times 2. And so you have 3 to the 0, which is 1. 1 times 2 is 2. And so that's how we can come up with our k value. So sometimes when you're doing problems like this, it is going to be a bit of trial and error to find the pattern that works for the problem. And again, I only found the equation on the first one just so you could kind of see how some of this ties together. Okay, so now we're kind of looking at this particular rule here, which is letting us go back and forth. So we have a function f of x, which is going to be exponential, and then we have another function g of x, which is going to be a log. And then we know that f and g are inverse functions to each other, which means if we test it through composition, remember that if we find the composition both ways, they should be the same. So let's talk about some of the things that we know and that we want to remind ourselves about. Let's say if we recall the output to a log is an exponent. That's from our changing to equivalent form. So let's get that in our list. So the output to a log is the exponent in exponential form of its equivalent form. So that's what we practiced in the last lesson. We also know in this particular situation, when we see f of x and g of x, that they're both functions. We also know from inverses, other things we know about inverses, that the graphs of inverse functions reflect over the y equals x line. And we know that if we look at the points on inverses, that the point x1, y1 on a graph of f would be the point y1, x1 on the graph of its inverse. So we can use our function notation here to designate the inverse. Remember, the negative one goes between the f and the h. So these are all things that we know going in to working more with inverses being exponential and logarithmic. You don't have this section in your notes, and that's okay. We were just kind of recapping some of the things that we do in fact know. All right, so example 3, we have f of x, which is 3 to the x, and we have g of x, which is log base 3 of x. Show that f and x are inverse functions to each other. So remember the rule that we talked about in compositions is the composition both ways has to equal x. So go ahead and find the composition of g of x with f of x, and then we're going to find the composition of g with f of x. So remember when I'm doing this, I'm going to write my f down and I'm going to write in the g equation, which is right here. So that's log base 3 of x. And then we're going to put that into where our x is here. So that's going to be 3. And then we're going to have log base 3 of x in the exponent. So what we're going to do at this point then is use our equivalent forms to rewrite that in a form that will help us answer this question. So to do that, remember that the base of the exponent becomes the base of the log. And then the output to a log is the power. So here's my power up here, which is log base 3 of x. So that means that I need to know the output because that's my argument, right? The output to an exponent is the argument. So then according to the property of equality then, if this is log base 3 and this is log base 3, then this output should equal whatever x is. So in this case, the output equals what? The actual x. All right, so that's how we're going to tackle that. So pause your video and do the composition of f of x with g of x. So f of x going into g of x. So here we go again. So we are taking our f function, which is 3 to the x, and we're putting it inside g. So then when I go to g, I'm putting 3 to the x right there. So that's what I have. Then when I rewrite it, the base of the log becomes the base of the exponent. The output to a log is going to, the output to the exponent is going to be the argument, and then we don't know what the output is. But since this is base 3 and this is base 3, with that equal sign in between, it means what's here for the output has to equal what is here for the power. So that means this one is x. So we have shown using our algebra skills this, and that's what we're seeing right here. For number 4, we have a portion of the graph over here on our graph, and that portion represents k of x, which equals 2 to the x. We're going to sketch a picture of the inverse on the same coordinate graph. So what does that mean? That means since k of x equals 2 to the x, and that's what's graphed, then I need its inverse. So its inverse, remember, is going to be, I can do k to the negative 1 of x. That's the inverse symbol. So what's the base of my exponent? 2. So that's going to be the base of my log. And then what's going to go right here? That's going to be the x. So when I graph inverses, remember domain and range trade places. So I'm going to come over here to my graph and I'm going to grab this point because this is k of x. And this point looks good, and how about this point? And so I will use those 3 points. So x and y, and so it looks like I am at negative 1, 1/2. I am at 0, 1, and I am at 1, 2. So those are the points that I am grabbing from my graph. And then we know when the domain and range trade places that my inverse graph for this table here then is simply going to be 1/2, negative 1, 1, 0, and 2, 1. And so then I'm going to go over here to my graph and I'm going to graph 1/2, negative 1, and I'm going to graph 1, 0, and I'm going to graph 2, 1. And I am going to rough sketch this in here. So it's going to kind of come around here, and it's going to do this. And then I can see, since this is my k negative 1 of x, I can verify and confirm that those are a reflection over, remember this is y equals x. And so that is reviewing what we talked about graphically. So the same concept on example 5, variations, but all the same. We are given an h of x value that's exponential, and it contains these 2 points. We want to find the average rate of change. So remember, that's the AROC of the log form over this interval. So we have an interval from 3 to 7. So the first thing that I want to do is figure out my points, right? So these are on the points of h. So h of x is going to have the points for x and y of 2, 3, and 6, 27. So if I'm finding the inverse, excuse me, h negative 1 of x, then my x and y's trade places. So now I have 3, 2, and 27/6. So I can find the A rock. Now remember, on my interval, we start with B, right? And then we go to A. So it's the f of B minus f of A over B minus A. In this case, we are talking H. So we're going to say H of B, just for our notes, minus H of A all over B minus A. So just so you can kind of tie that back to the formula that we've been using throughout the year. So I'm going to plug it in now. So remember that here is my log equation. So when I calculate my A rock, then I'm going to say log base A of 27 minus log base A of 3 all over 27 minus 3. So then I should be able to use what I know about the points here to actually come up with those values. So log base A of 27 is 6 minus log base 3 is going to, log base A of 3, sorry, is going to be 2, and then I subtract all over, and then on the bottom is B minus A, so 27 minus 3. So when I do the math here, I get 6 minus 2, which is 4, over 24. So my A rock is 1/6, and that's my average rate of change. Okay, so now let's kind of go over some characteristics of log functions and those relationships that hopefully we've been thinking about and building as we've over the last couple of days talking about logarithms. So basic definition in general form is f of x equals a log b of x. And so any log function that we learned about in Algebra 2, we said a and b are constants, a can't be 0 and b can't be 1, but they have the domain restriction of 0 to infinity because remember they have a vertical asymptote at the vertical axis. And then the range is everything, so everything will work. So those are the basic things carrying over from Algebra 2. So we spent a lot of time learning that information. And then now we're down here and we're just looking at the general picture of that term. So we can see the curve is going to be like this for this general graph, and that is if A is greater than 0 and B is greater than 1. So the reason that that is important is if we look at this equation, f of x equals a log b of x. So if a is positive, there's been no reflection over the x-axis. So that means it's going to start here and curve up. And remember that we have a vertical asymptote there in this particular case when up and down when x equals 0. Okay? Then over here, when a is less than 1, so think about that equation again. So if a is less than 1, then that makes that value negative. So this is a reflection over the x-axis. So when a is negative, it turns upside down. When a is positive, it's curving upright. Then in either case, we still have our vertical asymptote there because we haven't had any horizontal shifts. So here's just information, basic information once again about the logarithmic function. All right, so what's true about logarithmic functions? If we talk about increasing versus decreasing, then a logarithmic function always increases or always decreases, which means there is no relative or local extrema, unless maybe it's on a closed interval where we could be looking at the endpoints. And then we have concave up versus concave down. And so logarithmic functions are always concave up or always concave down, never both, and they have no point of inflection. Okay, then we have our end behavior, and in our end behavior, the logarithmic function in general form, as the input increases without bound, the output will increase or decrease without bound. Since logarithmic functions have a restricted domain, they are vertically asymptotic to x equals 0. So we talked about that right here. And as a result, the end behavior will occur at x equals from the positive direction. So you're going toward 0 from the positive direction. All right, so then we have our end behavior statements. And so we are focusing these statements to go from the positive direction to 0 of this function. Then the other end is either going to go to infinity or go to negative infinity. And then as we approach positive infinity of this log function, then that end is either going to go to positive infinity or negative infinity. So let's think about if we have this graph right here. And so it roughly does this, right, as a logarithmic graph, has a vertical asymptote right here. So then the limit as x approaches 0 from the right of the function a log b of x. So what is happening as it goes to 0? Then this is going to negative infinity. And then if we go to the other end of the graph, so we can say the limit as x approaches positive infinity of the function a log b of x, then what's happening over here, this function as we go to positive infinity is what the limit is on that side. So that's one example. We could also have another graph that's turned upside down like we looked at. This is my vertical asymptote, sorry about that, over here. And then we can have it like turning upside down, so it's kind of doing this. Then as we write those limit statements, we're going to have the limit as x approaches 0 from the right of whatever this log equation might be. And so as we approach 0 from the right, this time it's going to positive infinity. And if we have the limit as x approaches positive infinity, of this function, then what's it doing as it's going to infinity here? It's actually going out to negative infinity. So that's just going over those end behavior statements once more. Okay, so in example 6, we're just practicing. Okay, now we're going to look at example 6. And in example 6, we are looking at some of the characteristics that we've talked about in other functions or in other topics like we did in exponential. We're going to kind of go over characteristics. So we're going to look at the end behavior statements. We're going to look at whether it's increasing or decreasing and whether it's concave up or down. So let's start with A and B because those are already graphed for us. Your note page, for some reason, the names of the graphs got cut off, so you might want to add that to your note page. And then I'm going to ask you to pause your video, and you should be able to look at these graphs and determine the left end behavior, the right end behavior, whether it's circle, whether it's concave up or concave down, or increasing or decreasing. And keep in mind, right, we have some asymptotic behavior on here. All right, so pause that video and work through these two problems, problem 6A and 6B. Okay, let's see how you did. So remember that we're doing our left and right hand statements, so we're going to 0, which is where the vertical asymptote is. So the limit as x approaches 0 from the positive side. The name of the function is f of x, and so what is the y value doing? It's going to negative infinity. And then we're looking at it to the right of the graph, which is going out to positive infinity. So it's curving out to positive infinity this way. So as the limit as x approaches positive infinity of f of x, don't forget to name that function, we can't have any empty limit symbols, then we can see that it is also gradually getting higher and going out to positive infinity. The graph itself is concave down. And what is the graph doing as it moves, as the x, and then the function, as those x's get bigger, the function is increasing. All right, so now let's look at h of x. So we have that vertical asymptote, the graph is going this way. So as the limit as x approaches 0 from the right, the y value is going to infinity. The limit as x approaches positive infinity, moving out this way, then the y values are going to negative infinity. So this is concave up, and this is a decreasing function because as the x's get bigger, the y values get smaller. All right, so now we're going to kind of have to rough sketch a little bit to think about what's going on with these two. So we'll kind of talk through and get a picture and then pause again and answer the questions. So we know that this is a log base 3. We know that a is positive. So from our table of information that we looked at a moment ago, that means it's got to be doing something like this. We don't have to know specifics. We just want a general idea of what the graph looks like so we can determine those limit statements. Okay, so it's going to look something like that. It just means the 2 in front has been vertically stretched, so it's kind of growing a little bit faster. So what about this one? When I look at this piece right here, I see it's been stretched, but it's also been reflected. So if I have a graph like that, then it's going to be reflected over the x-axis. So this is turned upside down. So my graph is doing something like this. And again, you don't have to be super specific. I just want you to be able to kind of reason through what it might look like so you can give yourself a visual when you're answering your questions. So go ahead and pause your video and answer your left and right bound questions, your concavity questions, and your increasing and decreasing. Okay, so let's go through it. So as we approach 0 from the right, the function value is moving toward negative infinity. As we approach positive infinity going this way, the function values are moving toward positive infinity. This particular graph is concave down, and as x's increase, y's increase, so it's an increasing function. So this one was reflected over the x-axis, so we've got our picture we set up. And so as you approach 0 from the right, the limit as h of x approaches 0 from the right of, and name the function correctly, h of x is infinity. And then the limit as x approaches infinity, so as we go this way, then we can see the function values are moving down toward negative infinity. So this particular graph is concave up, and this particular graph is decreasing because as the x's get bigger, the y values get smaller, so that makes it a decreasing function. All right, our last problems here we're looking at in example 7, it says state the equation of the asymptote and then find the domain and range of the log function and use interval notation to state your domain and range. So again, give yourself a little bit of a picture. We know that the vertical asymptote on a log function is always on the vertical axis unless it's been transformed. And so which transformation would affect the placement of that asymptote? If we shift it up or down, is that going to change it being on or off the vertical axis? Nope. But if we shift it left or right, then that could change that. And that could also change the domain. So go ahead and pause your video. So this, give yourself a picture and then answer the question. So what I mean is just what we've been doing on the other problems. We're going to do a rough sketch. It is a log base 3. A is positive. It's stretched a little bit, so it might be getting a little steeper faster. The vertical asymptote on the main parent function, remember, is right here on that y-axis. So write the equation of the vertical asymptote, write the domain and range in interval notation. Pause your video. All right, let's see how you did. So the equation of the vertical asymptote is an x equals equation, and that's x equals at 0. The domain starts at the vertical asymptote and doesn't include it, so that's why we don't include the 0, moves toward positive infinity. The range is from the bottom, which is going forever and ever, ever, to the top, which is going forever and ever, ever. So the range is from negative infinity to positive infinity. All right, so on B, I want you to draw yourself a graph, sketch yourself a graph, and then answer the same 3 questions. So pause your video. Okay, so looking at my equation and all the time we spent in Algebra 2 studying transformations, hopefully we can recognize that this negative, when A is negative, it's going to be reflected over the x-axis, and it's going to have a vertical dilation by 5. Then inside is a horizontal translation, and so it's, remember, counterintuitive. So if this is x minus 3, then it's actually moving to the right 3. So I sketched a really quick graph. I said here it went to the right 3, so here's my new vertical asymptote. It has turned upside down, so take this one and flip it upside down. Gives you something like that. So then we can see the vertical asymptote is at x equals 3 right here. And then the domain is going to start at that 3 at that vertical asymptote, but we're not going to include it. And we're going to be moving out this way, so we go to positive infinity. And once again, it's negative infinity to positive infinity, because if this is growing forever in the positive direction and this is growing forever toward the negative direction, then that's going to include all values in the range. All right, one last one, same thing. Figure out what transformations you see, give yourself a rough sketch of the graph, and then answer your 3 questions. So go ahead and pause your video one last time. All right, well, C was a little trickier. I'm not sure if you remembered, but I hope you caught, because we've talked about this year, that when your B value is something other than 1, then you have to isolate it. So we have to divide out the 2, which means I have to divide this by 2 and this by 2. So I actually, inside here, I have x plus 3 halves. If you don't remember to isolate that B value, then it's going to mask what's happening here. This isn't a horizontal translation to the left 3. So if you didn't remember to isolate, you're probably going to might have a little bit of stuff wrong here, but hopefully that refreshes your memory. So we have the 8, which is going to be a vertical dilation by 8. We have the 2, which is going to be a horizontal dilation by 1/2. Remember, it's by the reciprocal. And then the plus 3 halves means we have a horizontal translation to the left 3 halves. So I went over to 3 halves here. That's where my asymptote is. A is positive, so it's not reflected upside down. So it's just going to curve something like that. So I can see that my vertical asymptote is at A equals negative 3 halves. Then I'm going from the negative 3 halves out to positive infinity for the domain. And then the range, since it goes forever in both directions, is once again negative infinity to positive infinity. All right, so that takes care of both of the topics 210 and 211. Make sure you're comfortable with the table work. Make sure that you do spend some time practicing and making sure that you know the information on the characteristics from the table. Most of that is a straight-on review from Algebra 2, except we don't talk a lot about this and this. So just make sure that you covered all your bases. Thanks so much, guys. I'll see you next time. Bye.